Hi, everybody. Okay, great. Well, today I'm going to talk to you a bit about the material in Chapter 9 and part of Chapter 10. As the chapter says, we're looking at remotely sensed images from above. We are moving into Section 2 of Part 2 of our Section 2 on remote sensing and imagery. Last week we learned about GPS and sort of got into a bit of satellites, even though it's not imagery, it's part of the whole satellite system that makes up our remote sensing and satellite imagery basis. So we will start with the basics right now. We're going to look at first at aerial photography and how it works. So get that to move forward. So what is remote sensing? It might be fairly obvious to some, but it is quite literally seeing something and figuring out what it is without actually touching it. So there we have light, it hits an object, that light reflects off the object, goes to our eyeballs take it in, send it to our brain, and our brain says, I know what that is. So if you compare that to what's actually happening in remote sensing, you take the eyeball and turn it into a camera. You take the brain, and turn it into the computer, and we have the remote sensing system. Fortunately, the physics of light and reflection still work the same. So, like so many things we study, I always have to add the caveat, this is actually a very complex field of study, dedicated on its own. So if you love it and you like it a lot, there's a lot you can do with it. You can study it way more in depth and become a super spy expert in remote sensing and satellite imagery. So just a brief history. Remote sensing is interestingly deeply tied to aerial photography, and which in essence captures the concurrent development of photography and flight, of course. I mean, if we put something in the air, you can better believe that we figured out a way to put a camera on it. The oldest existing aerial photograph you see here is of Boston, taken from 1860, and there are there was a picture older than that that predates it, but it was burned down in a fire, as things tend to go throughout history. So this is the oldest existing picture. This image here we see is actually from the Civil War, and they did use hot air balloons to try and do some reconnaissance and spying over the enemy lines. And I just discovered this delightful one recently, the Bavarian Pigeon Corps. So there was a very clever man who came up with the idea of putting little tiny cameras on pigeons. Pigeons were already being carrier pigeons and carrying messages and whatnot. So he decided to take it a step further. And it was used during World War One, to some good effect. I guess there was a lot of pigeons didn't fly in a straight path, and they tended to get eaten by other animals, so they weren't terribly consistent, but they were a good start. And I guess I also read that the CIA took over using pigeons to do spy reconnaissance, but I didn't really find much more beyond that. So something interesting to explore if you're into it. Like so many things that we see, so many bits of technology that we encounter, especially in GIST, it came out of military purposes, and by using it during World War I, especially, the technology really developed, and we sort of moved us forward quite quickly into developing the technology that we see today. Just a quick point, I just like to reflect for a moment on how quickly our ability to see the world has changed. It wasn't that long ago that we got up into the air and started to look down from above. So that picture from 1860, I mean, it's getting to be, 160 years ago now or so, but still, you think about where we've come from there until now, and it's remarkable. So how the Earth is viewed today. So we receive imagery data from satellites and from LiDAR systems. LiDAR stands for light detection and ranging, and we'll actually be studying that a little later this semester. We also still do aerial photography, but we do them from manned airplanes as well as UAVs. So up here we can see what an aerial photography airplane looks like. You can see the camera at the base there, and also in this one here, see a little camera there. And then these are our UAVs. This is a large one, and that's a very tiny one. Just a note on drones. Drones are more than just for military use. Esri has a whole set of software that you can use called Drone to Map for creating geospatial data from your drone imagery. And the imagery that we can use or we can obtain by using drones are useful in a wide variety of fields, including agriculture, transportation, architecture, surveying, engineering, crime scene investigation. And it's important as in addition to satellite imagery, because satellite imagery is less frequent and it's less precise than what you can get with a drone. Like a drone is so much more personalized. You can just send it up as you need it and get the images that you need and process them the same day. So a little closer look at some of the different kinds of aerial imagery that is out there. It is important to note that this imagery actually does get used in GIS, and when we start processing images or start looking at satellite imagery, it's often a combination of things. So it's a combination of aerial pictures or satellite imagery. This first one on the left is a color infrared picture, and we'll learn a little bit more in the next section about how that works, but essentially we're looking at the non-visible waves on the spectrum, color waves on the spectrum, and they give us images that read the health and quality of vegetation and the landscape in a different way, and they offer us different insights. And again, we'll explore that later. The second one is a vertical image. This is just saying that the camera is directly over the subject, and there's, in this case, in this picture, it appears to be very little distortion. That's because you're fairly high up above the subject, as opposed to, say, for instance, this one down here that's over, looks like probably somewhere in Manhattan, where you've got those tall skyscrapers, and the camera is actually quite close, and you get this kind of displacement of things as they sort of move away from your principal point. So this would also have a principal point, but it's probably just much less obvious than it is down here. Panchromatic simply means that it's grayscale or black and white. Oblique picture is what you see. It's just an image taken at an angle. And all of these can be used in varying ways in GIS and aerial image analysis. So last but not least, we have orthoimagery. So you may have noticed that, like on that picture of Manhattan, that the buildings have distortions because of the angle of the camera. There's always going to be a distortion no matter what you're looking at. But by orthorectifying, we can actually go in and switch around the kind of shape and angle of the buildings in the picture so that it looks like we're looking straight down on a continuous field of view. And you can see a little bit more of it here. This is a company, PCI Geomatics, that actually does post-processing on aerial imagery. And a little more subtle, but we see here we have this building. You can see the size of it kind of going down on the bottom and to the top and to the left. And over here, they've tweaked it. They've made it so that you can actually get the feeling that you're looking straight down on top of the building. So moving on to something else, that the next level of this aerial photography that is truly integrated with GIS are digital orthophoto quads, also called DOQ. They cover 3.75 minutes of longitude on the ground, and they're equivalent to a quarter of a USGS 7.5 minute topo map. If those things are unfamiliar to you, we will be going through in a little later sections about what that means. These maps are in fact, or these images are geo-referenced, so you can actually line them up with other maps that are geo-referenced to the same coordinate system. These are important because they give us a standardized orthorectified aerial imagery set that can easily be used in a GIS. And when I mean in a GIS, I mean like in a online mapping computer system that we'll be exploring in the future. So you can actually make measurements. So if you think about the fact that we have a geo-referenced map, such as back here, This means that we can actually then take this and figure out how far things are, how long streets are, how big buildings are. And this is called photogrammetry. So the science behind photogrammetry, however, involves determining the scale of the image. And that involves the focal length of the camera's lens and the altitude of the plane when the image was captured. And this is also important for helping us make accurate assessments of what we're seeing on the ground, especially as we do analysis with GIS. Something else that is important with satellite imagery and aerial imagery is being able to interpret images. Believe it or not, we actually have to interpret images all the time when we're working in GIS, simply because there are many times when we're working with images of landscape that don't have any mapping that exists, and we have to go in and do what's called digitization and actually draw out the shapes of the buildings, so the shape of a road. Or what I find very useful is if you're trying to create maybe a trail map of an area that has not official trails, but trails that have been formed by people walking off the beaten path, but always walking over the same pathway. And you can actually digitize that from an aerial photo onto a GIS. So there's actually, in the book, I'm not having you do the lab, but if you want to, you can do the lab for chapter 9. It is interesting. You actually do kind of a little puzzle where you try and figure out what the different aerial images are by using some of these skills, looking for tone, pattern, texture, and the like. So now I'm going to move into the first half of chapter 10, how remote sensing works. So I know we're quickly moving through this, but I think you'll find it interesting to take this in and then do the reading questions for the week. So as we discussed a moment ago, when we talk about remote sensing, we're talking about a camera, or the eye, but in this case the camera, taking in reflected light. And broadly speaking, what that means is that the sun is shining down on any object, on all objects, and that light is being reflected back up as reflected energy that is being picked up by the remote sensing satellite. And every energy wave that's picked up has a different kind of quality to it. But let's look a little bit more at what's coming out of the sun. We have what's called electromagnetic radiation. That is actually the light waves that are being emitted from the sun and hitting the earth and being processed by the ozone before it comes down. The EMR is responsible for many phenomena on Earth that are both visible and invisible to the human eye or senses, and it takes the form of waves. So you might remember this from high school science classes and whatnot, but we have the whole spectrum, types of radiation from radio all the way over to gamma ray, and the frequency and the size of the waves goes from very large to microscopic. So as we see here, radio, literally, what we get on the radio, microwave, what we cook our food with, infrared, we see this heat signature here. That's kind of how that's reading that. The visible spectrum, obviously what we can see with our eyes. Ultraviolet, think about getting sunburns. X-rays, see the cool black and white image of your hand or whatever else, bone is broken, down to the radioactive level. So we interact with all of these on a daily basis, and we see the visible ones, but even those we probably don't actively go, wow, look at that amazing reflected light. So let's narrow it down to this visible color spectrum briefly. As you know, we've got our red, orange, yellow, blue, green, indigo, violet, and on either side of those we have our infrared and our ultraviolet, again, which we kind of looked at in the last image, and I know we're all friends with that ultraviolet light. I'm sure all of us have had some kind of a sunburn in our life. And these are ultraviolet and infrared are very important to remote sensing and kind of the science behind imagery analysis. So this is something I like to contemplate a little more when you think about, this always just blows me away, the size of radio waves and the size of these gamma rays down here. Radio waves are huge. They're the size of buildings. They're the size of mountains. They're huge, huge arcs and waves running through the sky. And as we get down farther and farther, we see here our visible light spectrum. The light waves are the size of a pinhead. And as we move down our gamma rays, we get microscopically small. But I can remember when I was a kid learning about the size of radio waves, just sort of staring out the car window going, oh my God, no way. Can't believe it's actually that big. And that explains why you lose your radio signals when you go over mountains and valleys, and you lose, you imagine that radio wave is getting blocked and hit as it's trying to move through the landscape. So how does this all happen? Those EMR waves hit the Earth, do a variety of amazing things. They get absorbed by chemicals in the atmosphere, and they get absorbed by plants. Photosynthesis happens. But when the waves from the visible spectrum hit an object, three things happen. They are either absorbed to create heat, they're transferred and passed through to something else, such as like it passes through glass, or it's reflected, or it's a combination of things. And depending on the chemical and physical structure of the object, certain light waves of the visible spectrum are reflected in the form of color, or they are absorbed as heat. This is why, of course, black things get very hot, because they're absorbing all light, whereas white things tend to stay cooler. They're reflecting all of the light. So next time you're out, like this is very true with cars actually, you can run this test with cars. If you have several different cars around you in the open sunshine, middle of the day, I'm sure if you put your hand on each one, you could actually feel a variation in the temperature. So essentially what we perceive of as color is what is being bounced back to the human eye or the satellite sensor because of an object's particular spectral signature. And the spectral signature is what we as human beings process as what something is, what it looks like. And this is also actually how we understand what stars are made out of. It's that similar idea where the light that's coming to us is characteristic of certain kinds of atmospheric qualities and chemicals. So this is actually the end of the presentation for today. This is partway through chapter 10. Like I said before, there's actually no lab. I'm having you do an extended set of questions and a couple of additional hands-on activities. I hope you enjoy the subject for this week, and I look forward to getting into next week's material.